Hello and everyone. Welcome to the first webinar of the webinar series of the IEEE Sensors Council Optical Sensors Cluster. This cluster is a newly formed cluster within the IEEE Sensors Council. Um, After the webinar, you can definitely reach out to us on how you can be involved. Of course, we'd always love to see volunteers and many things and holding such activities. And we are thrilled to have the first webinar in this series. And today we have an excellent guest, excellent speaker, Dr. Cicero Martelli, who is a professor in the Department of Electronics at the Federal University of Technology, Pereira, and specializing in research and teaching in photonics and optical sensing. He holds a PhD in engineering from the University of Sydney. His career includes collaborations with the oil, energy, and transportation industries, as well as the founding of multiple photonic technology startups. With over 200 publications and 8 patents, his achievements have been recognized with several awards, including the IEEE, the coveted IEEE LEOS Graduate Student Fellowships and the Petrobras Inventor Award, which are really, really hard to come by. Congratulations to him on that, which he has received twice, not just once. He is currently the general co-chair of the IEEE Sensors 2028 conference. Without any further ado, we would like to get started with the first talk, with a talk on distributed fiber optic sensors. Professor Martelli, over to you. Thank you.
Thank you very much for the introduction, Ashwin. I would like to welcome everyone to this first presentation of this webinar series. I need also to thank Carlos for organizing this webinar series and for all the hard work he's doing on promoting optical sensing across the IEEE Sensors Council community. The talk we will be presenting today is on distributed fiber optic sensor systems. We will cover a little bit of the principles, discuss some of the challenges, and mainly focus on presenting the applications we have been working on for the last 10 years. So the summary, I will present our group, the Sensing Technology Group, cover these fundamentals, the sensing principles, what is DAS and operating at high and low frequency, and the DTS. I will introduce to some of you the Siphon group, which is works focused on solving issues regarding the offshore oil industry and the application of optical fiber sensors in such conditions. And I will cover several applications that we have been working on, both in lab and field tests. So our research group is composed by 4 leaders. I show them all here. We have several other doctors and students, PhD students, master students. I list the ones that are more related to the work that we are presenting here today. From all these, I would like to emphasize that we like to work with the heavy industry and the energy sector, but we also do some biomedical engineering and robotic systems. I have to say that we are kind of a classic research group within a technical university. So the talk here will cover applications and some of the principles of these 3 main technologies: distributed acoustic sensing, the DAS systems, distributed temperature and gradient sensing, the DTGS systems, and distributed temperature sensing, which are more common, the DTS systems, or more, let's say, traditional already, right? So the motivation for us to work on this area, Brazil is a large country. Our industry is fairly strong. We're the 9th economy in the world right now. And as a technological university, for us, it's very important to have some intellectual independence, and especially in this area of distributed optical sensing technology, which is important for one of the most important companies and business in areas and sectors in Brazil, which is the oil industry and Petrobras. So we also feel motivated to understand how we can deploy this technology in the field. and understand the challenges and what you have to do to overcome them and to be successful in these applications. And the main technology for us right now is the measurement, the capacity of measuring acoustic and temperature signals within offshore oil wells and the seabed and so on. We'll be showing some results on that work here today. A quick timeline where we started working with focused on distributed sensing systems, optical fiber sensing systems, back in 2015. But before that, of course, we had some experience on optical fiber sensors. I won't mention everything that is in this timeline for you, but I will say that in 2021, it was created a spin-off from our group, which is called Immermessen. We'll be showing results from Immermessen today. As you can see, Petrobras appears in several moments throughout this timeline, and there will be some very, very nice and new results that I will share with you today, which concerns the detection of whales in the South Atlantic Ocean. For the first time, it's done here, and some very out of the oven, I can say, results on seabed seismic within the Petrobras facilities. And all of this is done by using DAS or DTGS or DTS. So some sensing principles. Everything starts with the electromagnetic wave. I know that maybe some of you that are attending this talk are students, so I like to show the electromagnetic wave. Out of the properties of this wave, one that I like to emphasize most is the frequency. You can go from a fully transparent material to electromagnetic wave to a completely opaque material to electromagnetic wave by just changing the frequency of the wave. And several other nice stuff happens when you look into the frequency spectrum, or you are looking at the frequency features of the wave. Of course, this is not the only thing that you have to take into account. Intensity is also quite important, but I like to say that because sometimes the students forget to think about frequency, and is one of the most important features. But the light is not only defined as a wave, it is also defined as a particle. And together with the light component and the particle component, we see many things happening, many phenomena happening. And here I will talk about the ones that are interesting for us today. So the light, when it interacts with matters, you have reflection, transmission, absorption, and you also have scattering. And this scattering is better understood as a particle-like property of the light. And there are three scattering that happens when the infrared light interacts with silica, and which are important for us. The Raman scattering, the Brillouin scattering, and the Rayleigh scattering. The Rayleigh scattering is completely elastic, and it happens without energy conversion, and the scattered light has the same frequency as the source. As the Brillouin and Raman scattering, you have energy conversion, and then the scattered light happens to have a different frequency from the incident light or the source that you are pumping the material. The Raman scattering has some nice properties against temperature, and it allows us to measure absolute temperature, whilst the Brillouin spectrum, or scattering, sorry, allows us to measure temperature and strain. I have to say that the DTS, distributed temperature sensing systems, use the Raman scattering. The DAS and DTGS use the Rayleigh scattering, whilst the DTSS using Brillouin. I'm not going to be covering anything with Brillouin today, only Raman and Rayleigh scattering, based technologies. There is another piece of technology which is quite important for us, which is the optical time domain reflectometry. I know that many of you may have seen a OTDR in the field. It's very common today, and all the optical links use equipment like this one to characterize the quality of the link. It is based on the time of flight technique. You send a pulse out of a laser, and this pulse propagates down the fiber. As this light interacts with matter, part of the light is scattered, and it goes back to the receiver. And if you use time and you know the speed of light, you can know the exact position where the scattering is happening. So with these, you can build up a plot like this one, where you have the vertical axis the optical power, and in the horizontal axis you have the time or distance you can convert using the speed of light within the fiber. When you look into this plot, you can see several features. The first one that I would like to show you is the fact that the average signal is going down, which means that the intensity of the light within the fiber is going down, right? Because part of the light is lost as the scattering happens and the light returns, for example, to the receiver. And then you see some peaks and you see some drops. And the drops, they are regarded to, for example, bending, and the peaks to connectors because they are highly reflective points. You can have splices and other kinds of things. And you can see the end of the fiber where you don't see any signal being scattered and returning to the detector, and you see a high reflection point at the interface between, for example, silicon air, which could be the case here. So this piece of technology is very important because it allows us to localize things within the length of the fiber, right? And it uses the Rayleigh scattering. However, it uses a no coherent light source, which is a broadband light source. But when you look into using a very narrow line width light source, nice things start to happen. One of them is the possibility of using a phase or developing or building a phase sensitive OTDR. And this is what we will do now. We will use a phi OTDR to measure things. So schematically speaking, at the left of hand side of my slide here, you see a non-coherent light source that generates that allows us to build an OTDR and generates this kind of signal we're looking at the bottom here, right? When I change the light source and I put a high coherence one, I still have scattering, but you see that I have only one frequency. I represent this by the mix of colors or only red, for example. And the signal, the backscattered signal, it is a bit chaotic, right? When you look at it, for some of the applications, for sure you would prefer to have the left-hand side one instead of the right-hand side one. But I have to tell you that this signal, it looks like this because it is the result of self-interference of the light that's scattered at the same wavelength, at the same frequency within the different scattering centers in the fiber. And they interfere at the face of the photodetectors, and they generate this oscillations or this, as I said, noisy, chaotic kind of signal. But within this signal, there is a lot of information. You have the phase of the light that interfered, or the difference between the phase of the light at the different coherent scatter centers. You have the amplitude, and this is the kind of things that you're going to be measuring. So schematically, I know that this is a classic drawing of how these things work. You have an equipment, you have a fiber, very long lengths of fibers. We have been able to measure optical fibers of the length of 100 kilometers. And you have the scattering centers, right? So the light interacts, the pulse of light interacts with the scattering centers, and then you have backscattered signal. Okay, if you have a narrow band, means that every single scattering center will work like an optical source of the same frequency, right? So all of them are going to scatter light at the same frequency. If they have different wavelengths, then you have different optical sources representing in terms of frequency, representing the different scattering centers. And this is why you have an interference or not at the backscattered signal. So I'll cover very quickly here some of the theory and some small or very quick designs of DAS and the DTGS and also DTS for us to move straight into the applications where we will find more interesting things to see. So the phase sensitive OTDR that we work here at the Federal University of Technology, it's based on heterodyne detection. There are other designs. You can use Max Zehnder, for example. It's a very good one. But the important thing is that you want to beat the reference signal or the signal that comes from the local oscillator, which is the laser, with the signal that comes out of the fiber that you are measuring. If you do all the maths and you look into the intensity signal that you retrieve with the photodetectors, you will have any information on phase variation, right? And the phase variation, it will rely on several things, right? For example, laser initial phase, laser phase noise. So you have to have a very nice laser with a very stable line in terms of phase and amplitude. And also it has a component, which is very important for us, that depends on the external disturbances that can happen in the scattered sensors, centers. And when you look into this, you see that there is correlation with temperature and strain, and you can use this to get information. So this is the background information of how we measure sound. These photographs have about 10 years right now, but I like them because they show how simple, in theory, a DAS system can be. So it starts with a laser, a polarization controller, acousto-optic modulator, optical circulator, and photodetectors. And then you have some equipment that will allow you to measure the signal that you are generating. The oscilloscope is the first one that we used. Has to be everything kind of high frequency, right? So this is 1 giga samples per second oscilloscope. And then, of course, when you're working with sound and working with like fine detection of phase, optical phase, of course, all the electronics and has to have good performance against frequency. So to show you here a very simple plot of the oscilloscope measurement of the system when it's operating, you see the scope traces here, and then when you have an excitation, you see the amplitude of the signal changing, right? So this was the first time, this experiment represents the first time that we were able to really understand what we were doing, but we were measuring amplitude and not phase. And in the phase is where you find the better results and the better information. So we evolved from there to the system we have today, and I'll show it later. To build a temperature gradient sensing system, it's kind of only, I'll simplify a lot of things here, and it's just for you to look into the only thing you need to do is to be sure that the fiber will not have any kind of mechanical excitation, right? And you look into the low frequency part of the signal. I show here that the phase follows the same trend as the phase that we retrieve out of the system follows the same trend as the temperature variation. So in a very simple experiment, we just put a spool of fiber into a thermostatic bath, and you controllably change the temperature, and we were able to recover the temperature information, right? So if we evolve from this, you can do some nice temperature measurements. The point is that you cannot measure absolute temperature. This is one of the things that the industry and the research groups are working very hard right now in a way of being able to measure absolute temperature with the precision that you can get with the DTGS and the absolute temperature information that you can get from the DTS. I'm not showing you this here, but I can say that when you are looking at the temperature information that you can measure with the DTGS system, we can go down to microkelvin and maybe below microkelvin in not so difficult ways, right? So this is something important that people are working on and trying to get it to be not only variation of temperature or gradient of temperature, but also absolute temperature information. Quick image here to show from where we started. I mentioned before, 10 years ago, where we are. and we started moving into what we have today, 2025. And I mentioned that the group has a spin-off company called Immermessen, and this is the image of the interrogator that they are using right now. Okay. So here are some of the information about the specs. You see that I'm here saying that the gradient sensitivity is 100 millikelvin, but right now we have in the lab sub-microkelvin, also on the order of nanokelvin. The distance a couple of years ago was 10 kilometers, now is 100 kilometers. So I didn't update this. This is probably from 2023. Last time I used this slide here, so just updating it right now. So this goes to 100 kilometers, and this goes to below microkelvin. So a DTS systems is also based on OTDR, as I mentioned. The setup is fairly simple, and I'm showing here the same way I showed you before. So you can realize one just with a laser, couple of detectors, some modulators and things like this, and then you get all the information to your computer, and the information that you get has the Stokes and the Stokes signal, and if you do the mathematics, you can transform the Stokes and the Stokes into temperature. DTS is a very consolidated technology. It's been around for over maybe 30 years commercially, in the really commercially speaking, over 25 years or 20 years or so. But there's still opportunities, and for us, the big opportunity now is to be able to merge all the distributed temperature, acoustic, and temperature gradient into the same system. So this is the kind of thing you are working on right now. Okay. So I finished the basics very quickly. I would like to introduce you also very quickly the CIFON. CIFON is the International Joint Industry Forum. You see that it's composed mainly by oil companies and people and companies that develop technology to oil companies. And the aim of this forum is to promote the growth of fiber optic monitoring systems in upstream oil and gas industry, right? So we are part of CIFON, and this is where we get the challenges, right? So I mentioned in the title of my talk today that we're going to talk about the challenges, and CIFON brings the challenges. You see that a lot of companies go there and say, I have this problem, I have this, I have done that, and so that's where we have the ideas, and you understand how colleagues of ours are solving problems and for the solutions that I'm going to show some of the results very quickly. So talking about research and metrology and things like this, CIFON has developed a test bench for you to characterize DAS systems. So it's the only organization in the world that's doing this. So it's fairly important to show this. So if you want to compare the quality of the different DAS systems, there are maybe tens of companies today or even more selling DAS in the industry. You can use the protocol that has been developed by DAS to characterize it both acoustically and also against temperature. And we have, as members of this forum, we have been working on this, and now we were working on the development of test beds and test protocols for low frequency measurements, which is the more or less the frontier for the industry at this moment. Okay, so let's go into the best part of the presentation, I believe, which is the applications. First, I'm going to cover some of the applications that we have been working on within the university, and then I will show some of the results the people from Immermessen sent us to share with you today. So we do a lot of fluid dynamics. In the oil industry, we work with fluids, right? So it's gas, it's liquids, and so all this flowing within pipes coming out of the reservoirs, going up to the platforms or to the refineries, and then have to process all these things. So we do a lot of fluids. So for us, it's important to characterize fluids, and I will show you just some example of the slug flow measurement. This is the facility of the Federal University of Rio de Janeiro, where we carry on all the experiments that I'm going to show you today. And so we install the fibers there. They generate the controlled flows, and then we use this to calibrate our algorithms and models. So for those of you that don't know what slug flow is, it is like this. You just have a big bubble. It looks like a slug, and it goes inside of the pipe like this, like in a kind of periodic manner. And it can have different speeds of fluids, of air, of liquid. The bubbles have different size, and it can be quite complex. So what I'm showing you here is just one measurement where you have in the vertical axis the distance or the fiber length, so about 100 meters. And in the horizontal axis, you have the time. And you can see these bluish vertical lines, they correspond to the bubbles, right? And you can see the whole dynamic of the bubbles going through the pipes. For example, one of the nice things that you were probably one of the first ones to monitor this was the coalescence of the bubbles. So you see bubbles merging at some point within the pipe, right? So you can track the bubbles, the different bubbles, and you can see when they merge together, they coalesce. So this is the kind of results we use to characterize to learn how the fluid can behave within pipes, right? You have high frequency components here that are related to the pumps and to the other gears that are around. So there is more information. When you look into these, you can look into this only the deformation that happens at the pipes, but also you can look into the sound component that is generated by the flow, right? So I'll show you quickly more measurements here. You see the vertical, the inclinated lines, and several different speeds, as I mentioned. They have different features, and so we transformed all these measurements into algorithms that can be used in the field, where you have a DAS system recovering information for the flow, and then we know we can correlate the lab measurements with the field measurements, right? So here is to show you that we more or less measure very nicely within a nice plus minus 10 error against reference systems. Using DAS, we do something that we like. We like animals, so we call it horse seismic. This is our old results. Many of you may have seen it already. We just instrumented a long piece of fiber cable within a field where the horses are trained, and then we were able to detect the different gaits of the horse, depending on the speed and the animal. And so we characterize this. Was nice to do this back in 2020. We have also instrumented a borehole. This was the first time we look into information from a real system operating in the field. This is water borehole, but was the time when we were able to characterize flow, the different features in the flow, the different features of the pump. We could see the sound wave propagating up and down, and we could get different information from the sound wave, that depending if it was going up or down, because you also have Doppler taking place in these cases. We carried on some very early stage seismic measurements, and you could see that we were able to measure the sound wave generated by a rock hitting the ground, and we could see information about the structure of the well. We have, for example, here what we call sanitary seal 10 meters of concrete and rock, and you could see very clearly here the transition of these 10 meters when you only had rock after that. And so that was an early stage result that took us to the place where we are right now. And you see in the last presentation the kind of seismic you can do now. So we were also able to monitor large electric machines. This is one of the highest hydroelectric power plants in Brazil, or in our state. One of their machines is very, you can see here, it's a big machine. It has about 12 meters in diameter. You instrumented the starter of this machine with optical fiber, and we turn on a DTS system. And with that, we are able to measure the temperature profile of the starter as the machine was operating in real operation kind of thing. This kind of measurement is important because in this equipment where the power is very high and the voltage is also very high, you can have aging or wearing of the insulation. And when this happens, you may have a short circuit between the rotor and the starter, and this can really damage this machine, which is a big loss for the company. We say that hydroelectric generators like this one is a machine that transforms water into money. So imagine if we stop one, the size of the loss or that it represents to the companies. Now I'm going to show you some of the results that the colleagues from Immermessing shared with us. They use the same technology that I have been sharing today. All the technology that they are using was developed by us. Of course, they have implemented and evolved some of the features, but basically it's the same thing. So the acoustic optical transducer, which was developed by them, you can see here, it was a way of increasing the acoustic sensitivity of the cable for a specific application in Petrobras refinery. So they want to measure the sound produced by the steam leakages within the refinery. For those of you that have been to a refinery, you know that the steam leakage is a big problem, and it causes a lot of ambient noise and a lot of energy loss as well. So there are several pipes, and you can really put an optical fiber on top of every single pipe. So you had to find a way of measuring the sound, and from the sound, rebuilding the points, the positions where the leakages happened, and try to, out of the sound, measure the leakages. So localize and measure the leakages. So the solution was to develop this system or this component. You can see that on top of this structure here, you place this component. So you had about 30 sensors like these ones monitoring what we call the pipe rack, which is a big structure. And we were able to measure, I'll show you this first, and then I'll go back to that one. Sorry for the mess up with the order. But this is the environment where we were measuring. So this is the satellite image of the refinery. So with these microphones, over 500 meters, we were able to reconstruct the sound of the leakages, localize the leakages, and measure how much leakage was happening, and convert this leakage into energy loss, right? So just I speed up a little bit here so that you could see the environment where we were applying this. And this is the behavior of the system. So basically wrapped around a membrane, a piece of fiber, and then we were able to retrieve the vibration that membrane is suffering as the sound couples into the membrane. Here is the frequency response, so it's fairly flat, and the quality of the different sensors in the same fiber. So we believe that this design with transducer has a lot of potential, not only for acoustic, but for other types of measurements. And in some applications, they might go very well, right? It depends, of course, on the space you have available, but just the fact that you don't need, for example, for an application like this one, you don't need electric power, you don't need electric communication based systems. So it's already something very nice. Okay, so this is the steam leakage detection in this refinery. So this is application that has been developed by Immermessen. This is something that I find very nice. I mentioned in the beginning of the presentation. We have been able to do the first detection of a whale in the South Atlantic using optical fibers. So this is more or less where we were able to measure. I don't know from which parts of the world you guys are. So here is where you measure his Rio de Janeiro, Brazil, South Atlantic. And this is the signal we retrieved. For this measurement, we use the optical network that Petrobras has in the ocean. They have hundreds and hundreds of kilometers of fibers that put together or communicate all the infrastructure that they have. And we can show you here this distance by time measurement with the DAS systems, where you can see the V shapes, which is a characteristic of the whales when they are making sound. So you have lower frequency and higher frequency sounds. Here you have a frequency plot, right? Just to show you the kind of sounds that we characterize. This is the equipment in the field doing the measurements, and this is the map of the optical fiber installed in the field. These yellow dots show the historical measurements and detection of whales in the region. So it really shows that here is a region where the whales go through. I'm going to show you a map now to show you this as well. I would like to show you the sound. It wasn't working in the past. I'm not sure if you will be able to hear anything, but trust me that all these signals generate a very nice sound. So the importance of this here is what you call the blue corridors, right? And the blue corridors show the migratory routes that the whales do. And you see that off the coast of Brazil, you have one important one. But the view here, or the idea here, is that you can do much more than that, because if you have a look at the network of optical fibers around the world, and if you could just merge, I'm going to go back and forth in these two ones, just for you to see that you could very well use the existing telecom cables to monitor whales. And you could do much more than that if you actually plug in a DAS and a DTGS system in one of these. And this is one of the things that we're really working hard to be able to do, which is monitor the ocean and the features and the animals and everything that happens there by using these systems in the existing network. And by last but not least, this result doesn't have more than 15 days, and is the first seabed seismic done by us. Is in the middle of the Atlantic Ocean somewhere in Brazil. I cannot tell too much about this because of the relevance of this information for the industry, but I can show you that the vertical represents distance, and the horizontal represents time. And what you see here is the seismic wave measuring the seabed. Maybe the water column here, 1 or 2 kilometers, and you get the fiber down there. The DAS is connected to it, and then out of the seismic experiments, you were able to retrieve information like this. Okay, so with that, I finished the applications and the conclusions. A lot of opportunities for offshore applications, not only for offshore, but you have to have in mind when you're doing optical fiber sensors that they have two things that are important from my view perspective. First, they are very small, so they go well where everything is very small. Okay, good. But sometimes when things are very small, the cost is very low too. And then optical fiber sensors in general, they don't go well where you don't have much capacity of investment. So the other point where optical fiber sensors are killers is where you need to do measurements over very large distances. And then you look into this, the telecom cables that I showed you there, for example, or you look into offshore applications for the oil industry or for other kinds of industries. So this is more or less the mindset that I have when I look into optical fiber sensors potential. Plenty of opportunities to enhance performance of DAS, DTS, and DTGS systems, in both in terms of quality, distance range. All the measurements that I showed you, they have very good quality, but they can always be improved in terms of these things that I mentioned. Very important for everyone to do field trials. They bring a lot of information for us, and they allow us to do meaningful experiments in the labs, and I think that is what will bring everyone to the full evolution and potential of this industry. And nevertheless, technologies are out there for you to buy, but it still is high tech, and we know that for the full application of the potential of these technologies, the support from research groups or from specialized companies, it's very needed, and this is the kind of thing that, in our opinion, will make the technology more or less successful. Well, thank you very much, and it was a pleasure to present this to you today.
Thank you, Cicero. First, let's thank the speaker and applaud. So maybe we'll do it virtually. Oh, sorry. Let me do that. Thank you. Great talk. So we do have a bit of time for questions. Either you can raise your hand or unmute yourself and please ask a question. I'm also monitoring the chat in case anyone's typing. Any questions?
Yes. Please feel free to ask anything that I can answer, or you can send me email later on, whatever you may have a doubt or thing that I can help. I'll be more than happy to help.
I believe someone has raised their hand. Please go ahead and unmute yourself and ask the question. You should be able to unmute yourself. Those who are raising your, okay, let me call out Andres.
Hello, can you hear me?
Yeah, we can hear you. Please go ahead and ask your question, please. Andres.
Hello, this is
And then
Andres
we'll
Chavarria.
follow
Thank
up
you,
with
Cicero. It was an excellent presentation. I was curious in your acousto-optical transducer.
Yes.
If there's have been, are there publications that show how much fiber you need to put in the membrane, or what the diameter of that fiber needs to be for you to enhance the signal?
Yes.
Or how do you decide?
Yes, perfect. Thank you, Andres, for your question. I'll try to answer it in the best way possible. We have a patent on this, and we have at least one publication as well out there. If you email me, I can send them, right? But yes, this is a classic membrane system, acoustic system. So all the radius, the thickness, and the way it's anchored, and the materials, the stiffness of the material, all this is important. Also, the way you place the fiber inside is important. The amount of glue you use, the amount of fiber. So there are some rules of thumbs that we have developed, and I will be more than happy to show it to you.
Thank you.
Yeah. Abhinav, please go ahead with your question.
Hi, Professor. That's a very insightful presentation indeed. I have a question regarding low frequency analysis for seabed seismics. As temperature variation is also a part of low frequency changes, so does that affect your seismic wave analysis, or how are you able to use both DTS and DAS in the same time for any kind of offset compensation or something that is needed, or how effective it is to do that?
Okay, thank you for the question. I really cannot comment too much on this application, but because of the kind of relationship we have right now and the project you have right now, and the need that information to be not disclosure. But what I can tell you is that when you are looking into sound measurement, sound-based measurement, and into a temperature-based measurement, the frequency scale is different. So you more or less can isolate one signal from another based only on the frequency spectrum or range that each one happened. There are other ways that, or other things that you can do. For example, in a very large measurement, let's in the seabed, we're talking about kilometers, right? The temperature will probably change not only in a different time scale, but also over the entire, or over the long lengths of fiber at the same way, while sound not, right? Or the mechanical vibration not. So you can look into these different things, and this will help you to filter the influence of temperature into an acoustic measurement, for example.
Great, thanks.
You're welcome.
Great. We have a question on the chat from Shailendra Kumar Singh. How does the spatial resolution of DFOS impact the accuracy of slug flow detection?
Which measurements are there?
How does the spatial resolution of DFOS impact the accuracy of slug flow detection?
Sure. Yes, this like, oh yes, it is very important, right? When you are working with DAS, DAS is a very nice thing. The way I showed it to you, it looked very simple. It's more like very simple benchtop setups, and it looks like the mathematics is kind of simple. But when you look into the measurement itself, you see that the sources, I'll talk only about sound, right? You can have a very small vibration sound source very close to the fiber, or you can have a very large sound wave front hitting the fiber. So they are all sound and vibration, but the way you measure them is very different. When you look into, for example, specific measurements within pipes, in the case of the slug flow, you have vibration components and you have sound components. The vibration components, they kind of they travel a little bit far away from the source, not too much far away from the source, but the sound components, they propagate as if they were into a acoustic waveguide, right? So the way we increase the spatial resolution and you increase the sensitivity to detect the slugs is by looking into these two signals, vibration and sound propagation back and forth. But surely resolution, gauge length will be important on determining the capacity of retrieving the information from the slug flows.
Great.
So that I gave a very generic answer, but that's the best I can answer right now.
Yeah, that's great. Thank you. We have a raised hand from Maria. Maria Pontes, please go ahead and ask your question.
Yeah.
Unmute yours.
Thank you for the presentation, Cicero. My question is about the distributed sensing, acoustic or temperature. You have limitation by tens of kilometers. How is the basic strategy to sense areas in the ocean, for example? And another question, just to, and could you comment a bit more about the success? You comment about the success of the technology and the interaction with the company, please.
All right. Thank you for your question. So right now we are measuring fiber lengths on the order of 100 kilometers, right? We know, but this is with our technology. We know that in the industry, people have been able to go beyond that, right? One strategy, for example, from the technology maturity to where we are right now, if you put two channels in the same equipment, you have 100 kilometers to one side and another 100 kilometers to the other side, and then you have 200 kilometers, right? So these kind of things can be done, right? But technologically speaking, you would like to have, for example, the possibility of using optical amplifiers along the length of your sensing cable. There have been demonstrations where people use optical amplifiers and they are able to retrieve the information, right? Or if you could put more intensity in your laser, just in a special fiber where let's say you don't trigger the nonlinear effects that will mess up your signal. So there are some strategies that have to be investigated. Another one that's already existing methodology is using more than one laser, right? So there are systems that use up to 4 lasers, and that will also increase the length of the fiber that we can use. The DAS technology, it has a limitation concerning, or a trade-off concerning the length and the frequency range, right? Because every single trace is like one sampling of the acoustic wave. So if the time to go back and forth of the signal is too low, the frequency responses of your system is going to be very low as well, right? So this is about the length, right? As for the interaction with companies, well, we have been working with Petrobras for over 10 years. It has been very successful. It is very intense. For the students, for example, they know that's it's a very professional environment where we have to get things done and we have to get proper results and we have to get and we are not able to publish everything that you generate. So that's something that sometimes in a scientific career you have to think about, right, when you work with the industry, because the majority of the things you cannot publish, you cannot tell anyone what you did, and this is exactly the opposite when you are not dealing with company's money, right? But for us, it still is a big opportunity to face real challenging problems and to help the industry to grow, and we really like that.
Great. We have one more question on the chat from Mr. Welton. They're commenting on your presentation. Great presentation. Thank you. Do you think DAS with optical fibers could be a better technology to detect mass structures instead of using LiDAR or synthetic aperture radar, SIR? How better would it be?
To detect what? Sorry, can you please repeat that, please, Oshin?
To detect mass structures, MASS structures, or big structures or mass structures with big mass.
Okay, wow. All right. I will interpret this as, for example, structural health monitoring kind of things, something like this, maybe. I'm not sure, but like large structures. Well, the good thing about optical fibers is that they are made of a material which is flexible, small, like in diameter, and they can mimic the structure, so you can integrate them into anything, right? You can integrate them into material like metal, concrete, or you can screw fiber cables, you can weld fiber cables, you can do many things to integrate them, glue them. Of course, this expands the potential of the technology quite a lot, especially if you consider that, for example, against LiDAR. LiDAR is a beautiful technology, but if it rains, if you have smoke, if you have anything covering your signal, you don't have measurement. You don't have this problem with optical fibers. So I believe when we're talking about like high-end technologies like a LiDAR, of course you always have something that one technology is better than the other. But I think yes, DAS is competitive for a lot of applications. You are welcome.
Great. I don't see any more questions on chat. I don't see any hand raises. We still have time for maybe one question in the interest of time. None? Okay, I will assume there are no more questions. Maybe if you have any, you can take it offline with the speaker. You can directly email Dr. Cicero and connect, which is the main idea of these webinars. And we, again, let us all thank our speaker for today for graciously agreeing to open up the webinar series. This is part of the Optical Sensors Cluster of the IEEE Sensors Council. Thank you all for attending, and whatever zone you are in, have a happy rest of the day. Thank you. Thank you, Dr. Cicero.
Thank you, guys. Bye-bye.